We're going to begin the course Math 411 with a discussion of the integers, and this is part one, which includes the basic things we'll assume. So in any math course, you have to have a starting place, and this is the starting place for Math 411. First of all, the notation, at least some of the notation we'll be using. This capital boldface Z is the set of integers. These are the whole numbers, positive, negative, and 0. Capital boldface R is the set of real numbers. So we might describe the real numbers as the numbers represented by points on a number line. These are the numbers that you used in calculus and algebra. Capital boldface Q is the set of rational numbers. So these are the fractions. M over n, where m and n are integers, and n is not equal to 0. And if we use a superscript plus on any of these sets, that will denote the positive numbers in the corresponding set. So for example, capital boldface Z superscript plus is the set of positive integers. And similarly for the set of positive real numbers and the set of positive rational numbers. And another set that we will not use very often is capital boldface N, the set of natural numbers, 0, 1, 2, and so on. Okay, now the assumptions that we're going to begin with as our starting point. We will assume all the arithmetic properties of the real numbers. So any property of addition, subtraction, multiplication, and division that you know and learned in an algebra course, say, you can feel free to use in this course. For example, the distributive law. For all real numbers a, b, and c, a times the quantity b plus c is a times b plus a times c. And as you know, according to the conventions for leaving out parentheses, the parentheses on the right-hand side of this equation can be omitted. Properties of inequalities we will be using. For example, you know that if a and b are numbers and a is less than b, and if c is a negative number, then multiplying the inequality a less than b by the negative number c reverses the inequality. So that and every other property of inequalities that you've learned in your math education so far. Here's a property that you know about, I would guess, but it's a property you don't think about too much when you're doing algebra or calculus, the closure properties. So, for example, the real numbers, set of real numbers is closed under adding, subtracting, and multiplying. So what does this mean? This means that if you add any two real numbers, or subtract any two real numbers, or multiply any two real numbers, you get a real number as an answer. The real numbers are not closed under division. You cannot divide another real number by 0 and get a real number. But if you have two real numbers, a and b is not 0, then a over b will be a real number. So the real numbers are almost closed under division, with the exception of dividing by 0. What about the integers, the positive, negative, whole numbers, and zero? What operations can you perform on the integers and know that you will always get an integer answer? Adding, subtracting, and multiplying. Integers will always give you an integer, the same three properties under which the real numbers are closed. Let's try one more. What about the positive integers? Well, if you add two positive integers, you get a positive integer, but not subtraction, right? Subtracting two positive integers will not always result in a positive integer, but they are closed under multiplying. Multiplying two positive integers will give you a positive integer. So the integers are closed under adding and multiplying. And now the the final things that we'll assume are the greatest and least element properties of the integers. So these two properties are really equivalent to the technique of mathematical induction. So in your proofs course, for example, you may have learned how to prove statements by mathematical induction. Well, it turns out that in Math 411 it's more convenient to use the greatest and least element properties. And here they are. The greatest element property: if you take a non-empty subset, capital A of the integers, which is bounded above, then it has to have a greatest element. And the least element property: if you take a non-empty subset of the integers, which is bounded below, it has to have a least element. So these do not apply to the empty set. Right? The set A, capital A, has to be non-empty in both cases. Okay, a few definitions, probably not necessary, but just to make sure we're talking about the same concepts. But bounded above, a set capital A of numbers, of any set of real numbers, is bounded above if there is a real number b which is greater than or equal to all the elements of capital A. And if you find such a b, it's called an upper bound. And the definition of bounded below is similar. Capital A is bounded below if there is a number c which is less than or equal to every element of A, and c is called a lower bound. Greatest element, A sub g, is a greatest element of the set of numbers A. If it fulfills these two requirements, it has to be in A, right? To be a greatest element of A, you have to be in A. And secondly, A sub g has to be an upper bound. It has to be greater than or equal to every element of A. And least element is defined in a similar way. Must be in A, and it must be less than or equal to every element of A. Let's try a couple of examples. So the greatest and least element properties are about sets of integers, but in this example we'll be looking at a set of real numbers. So the greatest and least element properties don't necessarily apply. Okay, so capital A is the set of real numbers that are greater than or equal to 1 and less than 5. You probably know how to write this using the interval notation. In interval notation, it would be a left square bracket 1, 5, right parenthesis. Okay, so 5 is an upper bound for this set of real numbers. That's sort of built into the definition. Every x in the set has to be less than 5. And so is any number greater than 5. 1, or any smaller number, is a lower bound. That's also built into the definition. One is the least element. 1 is in A, right? 1 is less than or equal to 1. And as we've seen, 1 is a lower bound. And A has no greatest element. Right? 5 is not a greatest element because 5 is not in A. Okay, let's go back to an example where we are talking about sets of integers where the greatest element and least element properties do apply. Okay, so here capital A is the set of integers, q, which are greater than or equal to 0, and for which this inequality, 75 minus 13q greater than or equal to 0, is true. So A is a set of integers. That's built into the definition right here. And what we would like to do is find a lower bound for A, an upper bound for A. Let's notice before we start that capital A is non-empty. There is something in A, maybe more than one thing, but an easy thing. An easy number is 0, right? The number 0 satisfies this inequality, and the second inequality, when you replace q by 0, is also true. So we want to find a lower bound, we want to find an upper bound. Once we've found an upper bound, the least element property will guarantee us that capital A has a least element. And once we've found an upper bound, the greatest element property will guarantee us that A has a greatest element, and we want to find those. Okay, so just a reiteration of how the set builder notation that I've used here in the description of A, how that works. So what are the criteria for a number q to be in the set capital A? It has to be an integer, and it has to satisfy the two inequalities following the colon. Q greater than or equal to 0, and 75 minus 13q greater than or equal to 0. The second inequality is going to be easier to deal with. That's the 75 minus 13q greater than or equal to 0. Be easier to deal with if we solve for q, which is a fairly easy thing to do. We will subtract 13q from both sides, and then divide both sides by 13. And I have also rewritten the inequality using less than or equal to instead of greater than or equal to. So now we can rewrite the conditions. We can rewrite the conditions for being in capital A. Right? Q has to be an integer. Q has to be greater than or equal to 0. And we have a simpler form of this second inequality. So Q is an A if and only if Q is an integer, and 0 is less than or equal to Q is less than or equal to 75/13. So now we have a much easier description of A, easier to deal with. A is the set of integers which are greater than or equal to 0 and less than or equal to 75/13. Okay, from this description there's a fairly obvious lower bound and upper bound. Right? 0 is a lower bound. That's built into the definition right here. Every element of A has to be greater than or equal to 0. 0 or any smaller number is a lower bound. 75/13 is an upper bound, or any larger number. Smallest element. Well, 0 is the smallest element of capital A. It's in A, because it's an integer that fulfills this inequality. Oh yeah, so one thing I should mention, we will see that there are also some upper bounds that are smaller than 75/13. All right, so 0 is the least element of A. And now what about the greatest element? Not 75/13, because 75/13 is not an integer which is required for being an A. The greatest element of A will be the biggest integer which is less than or equal to 75/13. Well, 75/13 is between 5 and 6, so it looks like 5 is the largest integer fulfilling this second inequality. Greatest element of A is 5. So this concludes our discussion of the basic assumptions that we will be making.